Okay, let's see how you're doing so far on these. I realize that some of you haven't had a chance to finish them yet. We're going to start out with number 1 here. When we do a power, so we've got 3x to the 5th, y to the 3rd, and we're raising it all to the power of 4. What do we do with the 3 here? Not times 4, but to the power of 4. So 3 times 3 times 3, which is 81. Perfect. What do we do with the x to the 5th? That becomes x to the 20th. There we do multiply the powers. We have a power of a power, we multiply the powers. Y to the 3rd to the 4th power? Y to the 12th. Good. So now over here, going to the 3rd power, 2 to the 3rd power is going to be 2 to the 3rd power. 8. There you go. A to the 12th to the 3rd power. So it's going to be you multiply the powers when you do a power of a power. So 12 times 3 is 36. And then y to the 45th. Good. Moving down to our roots. Same type of thing. You apply the root to the number. What's the square root of 49? 7. Good. The powers then, if we were raising it to a power, we would multiply the powers. But when we're doing a root, we divide. So a square root, we're dividing by 2. So x to the 10th becomes x to the 10 divided by 2 is 5. Good. Y to the 24th becomes y to the 12th. Perfect. When we do a 3rd root, we have to do the 3rd root of 27, which is 3. 3 times 3 times 3 is 27. A to the 15th, what do we do to the power? It's going to be divided by 3. Good. So that's a to the 5th, and y to the 4th. There we go. Let's just review a few more of those. I think you guys need a couple more to be sure about them. So let's do this. Okay, so here we've got a couple of things going on. Inside the parentheses, we're multiplying. So the first thing we have to do is we are going to multiply these two numbers. So I'm going to multiply the counts, the numbers. 5 times 3 makes what? 15. Then I multiply each variable. A to the 5th times a to the 3rd is a to the, careful, it's going to be the 8th. When we're multiplying exponents with the same base, so it's a and a are the base, we add the powers. 5 plus 3 is 8. So then it's going to be b to the 5th. Good. 3 plus 2 is 5. Now we've got to raise it to that power of 2, the squared that's out here. Well, 15 squared is 15 times 15, or not 30. 225. There we go. Now, a to the 8th squared So a to the 8th becomes a to the... When we're taking it to a power, we multiply. So 8 times 2 is 16. And b to the 5th squared becomes b to the 10th. Very good. I'll give you an easy one. What's the square root of x to the 24th? X to the 12. Very good. How about the square root of 16, x to the 12th, y to the 4th? We have to do the square root of the number. What's the square root of 16? 4. Square root of x to the 12th? X to the 6th. And square root of y to the 4th? Y squared. Perfect. Of course, this is a cubed root. What's the cubed root of 8? What number to the power of 3 equals 8? 2. Perfect. Now how about the cubed root of x to the 6th? X to the 2. We divide by the 3. Good. And then y to the 5th. 15 divided by 3 is 5. Perfect. You're getting there. Give you a hard one? Well, let's see what I can do here. We'll do the square root of 12 x to the 5th, y to the 17th, times 18 x to the 11th, y to the 9th. So again, we got to do the multiplication inside here first. What is 12 times 18? 216. Good. We have x to the 5th times x to the 11th. There you go. When you're multiplying, you add the powers. Very good. Then y to the 17th times y to the 9th. 26. Very good. So, you got a square root. Square root of 216 is 14.69. Perfect. How about the x to the 16th? Square root of x to the 16th? X to the 8th. Square root of y to the 26th? Y to the 13th. Perfect. Okay. That's a really good question. It all depends on what you're doing. If you're in statistics, there are standard rules in statistics for means. You go 1 digit, 1 place value past the data for means and measures of center. For standard deviations, you go 2. For my quizzes and stuff, unless it's specified what it is, I would have accepted that as 14.7 or 14.69, either one.
Thank you.
You bet. Here's a tough one for you. give that one a shot in your notes quick. I'll give you a minute to see if you can come up with that one. Okay. I see a couple of you are still working, but let's go ahead and see how you're doing so far. So here we see parentheses. Parentheses should always tell us do something here first. First question we always ask with the parentheses is there anything we can do inside the parentheses? So for this first one, is there anything we can do inside that set of parentheses? No, I cannot combine 4x and negative 2y because they have different names. I'm trying to subtract them, that doesn't work. So the second question, is there anything that needs to be done to the parentheses? And it is being multiplied by the 6x. So what is 6x times 4x? 24x squared, very good. 6x times negative 2y? 6 times negative 2 is? Perfect, negative 12xy. Now we move to the next set of parentheses. Again, there's nothing we can combine inside there with addition. So we're going to look at multiplying the parentheses by 3. Now it's a plus here, so it is a positive 3. So 3y times 7x? 21xy. Now it's positive, so I'm going to put a plus in front of it. 3y times 4? 12y. Again, it's positive, so I put a plus in front of it. Now I've got the negative 2y, and I've got an x squared. Now looking at this, I have to see if I can combine anything. Is there anything I can combine with my 24x squared? The x squared, so what do I get? Perfect, 25x squared. How about with the negative 12xy? 21xy gives me, careful, negative 12 and positive 21. Positive 9xy, there you go. Now I've got the 12y and negative 2y make. What's 12 and negative 2 make? 10, there we go, 10y. Did anybody actually get that on their own before I did? Getting there? Okay. Well, the next thing we want to talk about, we want to talk more about these powers. We've talked a little bit about combining powers of 10. I want to actually specifically look at the powers of 10 themselves. 10 squared, we've already said, is what? 100. 10 to the power of 3 is 1,000. 10 to the power of 4 is 10,000, and so on. 10 to the power of 5, of course, 100,000. You'll notice here there's a relationship between the power of 10 and the number of zeros. 10 to the third has 3 zeros. 10 to the fourth has 4 zeros. If I were to multiply 10 to the fifth times 10 to the third, we know that that's going to come out to be 10 to the what power? The eighth. And if we look at our zeros, it works out exactly the same way. When we multiply numbers with zeros, we just multiply the leading digit, the non-zero digit. 1 times 1 is 1. And then we add up all the zeros. There are 8 zeros here. So our knowledge of multiplication with zeros and our powers of 10 does confirm what we've been doing with our exponents on our numbers. Now to keep going, of course, 10 to the power of 1 is what? 10. Anything to the power of 1 is itself. 10 to the power of 0 is? What's 10 to the power of 0? It's 1. Very good. Anything to the power of 0 is 1. Now that's something to make a note of and to keep in the back of your mind, because I might have a little bit of a twisted sense of humor sometimes, and you may at some point in the future see a problem on a test or a quiz that might look something like this. What would that equal? 1. Why? Because all to the power of 0. That's how math teachers amuse themselves, by the way, as we watch people work on that for half an hour before they realize that it's just a 1. Well, we are math teachers. So now I want to look at what happens when we have 10 to the power of negative 1. What does that equal? What does that mean? A lot of people say it should be a negative number. Point 1 is what your calculator tells you, right? If we look at our pattern here, just like we did when we were multiplying negatives, when we were starting with a base of 10 in our exponent, every time we reduce the power by 1, the result here is divided by 10. We went from 3 down to 2. This was divided by 10 to go from 1,000 to 100. Even here, we went from 1 down to 0. We divided by 10. 10 divided by 10 is 1. That pattern continues. 10 to the negative 1. Well, 1 divided by 10 is 1/10. 10 to the negative 2. Dividing by 10 again is 1/100th. 10 to the negative 3 is 1/1000th. And you'll see a connection there between our negative powers and our positive powers. 10 to the negative 3 is 1/1000. 10 to the third is just 1,000. So that means is 10 to the negative 3 is 1 over 10 to the third, or it's what we call the reciprocal when we were dealing with fractions. A negative power is just a reciprocal. So 10 to the power of negative 5 is just the reciprocal of 10 to the 5th. So if we go back to looking at our place values again, and I know we've discussed these in a few different contexts. Our place values, the 1's place is just 10 to the 0. 10's place is 10 to the 1. Hundreds is 10 squared, or 10 to the second. Thousands is 10 to the third, and so on. The 10th place is 10 to the negative 1. Hundredths is 10 to the negative 2, 10 to the negative 3, and so on. So if we put in a number, let's say we put in 2,800,000. We a lot of times will abbreviate that by saying 2.8 million. Well, there's another way we'd express that place value instead of million. We could just say 2.8 times 10 to the 6th. So what we have done is we've taken that first digit, we've named its place value, the 10 to the 6th. Then we put the decimal point after that and express the rest of the number. This, of course, is our scientific notation. And this is actually why numbers are expressed the way they are in scientific notation, is we are naming the place value of that first digit. So if I have 74,000, if I want to express that in scientific notation, I take that first digit, the 7. I'm going to put the decimal point after it, so that's 7.4. And the 7 is in the 10 to the 4th place value. So 7.4 times 10 to the 4th. Likewise, if I have a decimal, let's say I have 0.00081. I take that first non-zero digit, the 8. I'm going to put the decimal point after it. Then I'm going to name the rest of the digits. 1 is all that's left. And then I name the place value of that 8, which is in the 10 to the negative 4th place. Now, this is the formal way of converting numbers into scientific notation. Now, we were all taught shortcuts for doing that. And that shortcut looked like this. You know, 7,800,000, rather than saying that 7 is in the 10 to the 6th place, what we were taught to do is this. We want to put the decimal point after the first non-zero digit. And the decimal point started at the end of the number right there. We moved it to here, so it moved 1, 2, 3, 4, 5, 6 places. So that means it's 10 to the 6th. So the question is, how do I know if that's -6 or +6? Well, you're probably taught to memorize if you move the decimal to the left, it's positive. If you move it to the right, it's negative. Well, it's really easy. You know that this side of the decimal point is the positive powers of 10. That has to be a 10 to the +6. Likewise, this one, first non-zero digit is the 9, so we're going to express that as 9.7 times 10 to the decimal point starting out here, and we want it to be here after the 9. So we're going 1, 2, 3, 4, 5, 6 places again. But this is the negative powers of 10 place values over here, so it's -6. So in your notes for me, I want you to convert these. $390 million, put that into scientific notation. And 0.000053. So, of course, the 390 million is going to be 3.9. Put the decimal point after the first non-zero digit. Times 10 to what power? The 8th. Good. 1, 2, 3, 4, 5, 6, 7, 8. You are correct. 10 to the 8th. Over here, again, it's going to be 5.3. We put the decimal point after the first non-zero digit. It'll be 10 to the -5th. Good. 1, 2, 3, 4, 5. So it is 5, and we're on the negative power of 10 place values over there. What if this is -310,000, and I want to convert it into scientific notation? Does that negative affect my power of 10 at all? Say no. No, it doesn't. It's going to be a negative 3.1, but the power of 10 is not going to change. We're going to start here and go 1, 2, 3, 4, 5. That is still 10 to the positive fifth. Just like if I have .00039, negative 0.00039, that is a negative 3.9 times 10 to the perfect, negative 4. So the negative on the number does not change the power of 10 at all. All it does is makes this number out in front negative or positive. So let's convert the other direction. If I have 7.2 times 10 to the negative 8. So I start out with my 7.2. I have to move my decimal point because the power of 10 is an 8. I have to move it 8 spots. But do I make the number bigger or smaller? Well, it's a negative 8, which means that this is a small number. I have to make my number smaller by moving the decimal 8 spots. So 1, got to add a 0, 2, 3, 4, 5, 6, 7, 8. There's where my decimal point ends up. So that is point 1, 2, 3, 4, 5, 6, 7, then the 0.72. Or if we have 9.5 times 10 to the 7th, I take my 9.5. This is a positive power of 10, which tells me this number has to get larger. So I move it 7 spots, making the number larger. So I go 1, got to add a 0, 2, 3, 4, 5, 6, 7. So 95 million. Any questions? So that is our scientific notation. So we can convert from standard notation into scientific notation, and we've converted from scientific notation back into standard notation. There is another notation out there that a lot of people don't work with, but it's very handy in electronics and a lot of other fields, called engineering notation. And what engineering notation is it's a variation off our scientific notation that loosens up some of the rules and tightens down on others. In scientific notation, you could only have one digit in front of the decimal point, and it couldn't be a 0. But your power of 10 could be any number. Well, in engineering notation, you can have 1, 2, or 3 digits in front of the decimal point. But your powers of 10 are limited to multiples of 3. So in other words, 0, 3, 6, 9, 12, 15, or negative 3, negative 6, negative 9, and so on. So if I have $320 million, and I want to put it into engineering notation, not scientific, but engineering, I have to move my decimal point 3 spots at a time. So I go 1, 2, 3. Can I go 3 more? Sure can. 4, 5, 6. Can I go 3 more? No, if I went 3 more, there wouldn't be any digits in front of the decimal point. So this is 320 times 10 to the 6th. So how about this one? I move my decimal point 3 spots. 1, 2, 3. Can I go 3 more? Your first instinct is to say, no, I can't. But right now, are there any digits in front of the decimal point? No, there's not. So I have to go 3 more. 4, 5, and I have to add a 0, 6. That's 290 times 10. Of course, that's the negative place value, power of 10 place value, so it's 10 to the negative 6. So for this one, what's it going to become? I go 3, 1, 2, 3. Can I go 3 more? Yep, 4, 5, 6. I've got a digit in front of my decimal point, so I can stop there. So I get 5.7 times 10 to the negative 6, because it was in the negative powered place values. So 750,000. I go 1, 2, 3. Can I go 3 more? No. So that's 750 times 10 to the third. So putting a standard number into engineering notation is a little bit trickier because we have to worry about going 3 spots at a time with our decimal point, keeping that power of 10 as a multiple of 3. Going the other way from engineering notation back into standard really isn't tricky at all. Let's have 52.7 times 10 to the 9th. How far do I have to move my decimal point? How many places? 9. Am I making the number smaller or bigger? Bigger. It's a positive 9. So I go 1, then I have to add zeros. 2, 3, 4, 5, 6, 7, 8, 9. So that is 52 billion, 700 million. We might have 3.9 times 10 to the negative 6th. So are we making this one smaller or larger? Smaller because it's a negative power, and we're going 6 spots. So again, we move 1, and then we have to start adding zeros. 2, 3, 4, 5, 6. So it looks like that. So the question comes up, why do we want to mess things up with from scientific notation by introducing this engineering notation? Well, engineering notation is how our metric system works. Now I'm going to use electronics here for a second. This should be electrical power if you're doing the electrical side of wiring a house or whatever. When we're dealing with electrical, we don't use all of our metric prefixes. We only use the main ones. Like you might have a volt. Helps if I can spell. A volt. Well, we don't use decivolts and centivolts. We jump our 3 spots right to millivolts. Well, if we think of the volt as being 10 to the 0 or 1, a millivolt is 10 to the negative 3. It's 1/1000th. If we kept going, we'd get to microvolt. Micro is 1 millionth, or 10 to the negative 6. We can keep going to nano, which would be 10 to the negative ninth, and pico, and femto, and so on. Going larger, again, we don't have deca or hecto. We jump right up to kilo. A kilovolt is 1,000 volts, so that's 10 to the third. Then we have mega. A megavolt is 1,000,000 volts, or 10 to the sixth. So if I'm going to do operations, one of our formulas that we have for electronics is voltage is equal to current times resistance. If I have a current of 3 amps and a resistance of 5 ohms, I'm going to start being sloppy with the ohm symbol and just do that. The voltage would be the 3 amps times the 5 ohms. We multiply the counts. 3 times 5 is 15, but we also multiply the names. An amp times an ohm ohm is defined to be a volt. So our voltage is 15 volts. Well, back to our prefixes up here. It's not uncommon to have a current of 3 milliamps and a resistance of 2.8 kilo ohms. So what we're working with here, 3 milliamps is really 3 times, milli is 10 to the negative 3 amps, times 2.8 kilo ohms, that's 2.8, kilo is times 10 to the positive 3 ohms, and now we can do operations with this. We're going to multiply. 3 times 2.8 is 8.4. Now we did our multiplying with our powers of 10 a little bit last week and a lot on Wednesday. 10 to the negative 3 times 10 to the third. Okay, guys. I know. You'll live, I'm sure. So negative 3 plus positive 3 is 0. That's going to be 10 to the 0. Or just 1. So that's 8.4 times 10 to the 0, or just 8.4 times 1. Then an amp times an ohm is a volt. So our voltage is 8.4 volts. We're going to look more at doing operations with the engineering notation after we do operations with our scientific notation. So that's going to be our next step, is to look at operations with our scientific notation. We have our rules for addition and subtraction, and for multiplication and division. They all are defined off of the count and the name. We said that when we were adding whole numbers, like 3,852, that each digit had a count and a name. Like this 8 was really 8 hundredths. That the place values are the names of those digits. Well, in scientific notation here, what part of this number relates to a place value? Remember, we did out the number lines earlier. We labeled them with powers of 10. 10 to the 7th is the 10 millions place. So the power of 10 corresponds to a place value. So the power of 10 is the name of a number in scientific notation. So the 3.8 is going to serve as our count. So a little bit of a review, when we add numbers, when we add numbers, we first of all must have the same name. And then when we go to add them, we combine the counts. We're adding, so we combine the counts with addition. And we also combine the names. That puts us up about at our break time. You guys, let's go ahead and take our break here. We come back, we'll start doing the addition. So about 3 minutes, so about 2:47, we'll start up again. Okay, it looks like we got most people back here. We're missing, it's like one or so yet, but let's go ahead and get started. If you guys want to unmute your mic again. Okay, so remember, when we add, we must have the same name, and we'll combine the counts, and then also combine the name. So with our numbers in scientific notation, that means we're going to have to start out with the same name, means we have to start out with the same power of 10. So let's say we have 3.2 times 10 to the 8th. Plus 5.1 times 10 to the 8th. First of all, I should point out the parentheses here are not telling us to do something first. They're not really an enclosing symbol. They're a separator, kind of like when we had, 8 plus a -4. They just kept that -4 separate for us. That's all they're doing here. They're not telling us to do something first. They're just separating out our two numbers. Second, we do have the same power of 10, which means we have the same name, so we can add these numbers. And when we add, we combine counts. So we're going to do 3.2 plus 5.1. 3.2 plus 5.1 is 8.3. And then what power of 10 are we going to have? Times 10 to the what? Well, when we add numbers, I wrote this down wrong here, didn't I? We don't also combine the names when we add numbers. When we add numbers, we combine the counts and we keep the same name, don't we? So this is going to stay 10 to the 8th. So let's look at some more examples. Let's say we have 5.8 times 10 to the 12th plus 7.4 times 10 to the 12th. So we will combine the counts. What is 5.8 plus 7.4? $5.8 plus 7.4 gives us 13.2. There you go. Times, you had the right idea, times 10 to the 12th. Remember, we keep the same name. Now, we're dealing with just scientific notation here right now. So what's the problem with this number at this point? Right now, there are 2 digits in front of my decimal point. I can't have that. I have to move the decimal point over right here to make that 1.32. Now, if I move my decimal point, I have to adjust my power of 10. So I move the decimal point one spot. My power of 10 either has to go up or down by 1. To tell what it needs to do, we look at this number. Did this number get smaller or larger? Well, we went from 13 to 1. It got smaller. So the power of 10 has to get the opposite, larger. So 12 plus 1 is 13. You can hold hands after school, guys. Okay. So we might have 8.5 times 10 to the -9 plus 7.4 times 10 to the negative 9. So now again, we have the same power of 10, so we have the same name. So we can go ahead and add 8.5 plus 7.4 is 15.9. Good. Times 10 to the negative 9. Now we're going to have to adjust this again. What's this going to become? 1.59 times 10 to the
negative 10.
Be really careful here. I say this number got smaller, so the power of 10 gets larger. Negative 9 plus 1 is negative 8. It's backwards of what you'd think because it's negative. So now what do we do if we don't have the same power of 10? What if we have 7.32 times 10 to the 13th plus 9.4 times 10 to the 12th? Well, generally, we adjust those to the larger power of 10. Just like with fractions, we have to change their name to make them the same. So this one, the 7.32 times 10 to the 13th, will not change. That's already the bigger power. This one, however, is going to become times 10 to the 13th. So now it's just the opposite of what we were doing here. The power of 10 got larger. What has to happen to this part of the number? Got to get smaller. So we went from 12 to 13. That's going up by 1. This decimal point moves 1 spot to make it smaller. So that's 0.94. So now we add 7.32 plus 0.94 is 8.26 times 10 to the 13th. So let's look at 8.7 times 10 to the negative 10th plus 9.53 times 10 to the negative 9th. Which is our larger power of 10? Be very careful, they're negatives.
Negative 9.
10 to the negative 9. So that number is not going to change. This number has to change. Power of 10 got bigger by 1, so this number is going to become 0.87. It gets smaller by 1 place value, right? So now we're going to add our counts. 0.87 plus 9.53 is 10.4, right? Times 10 to the negative 9th. Are we done?
No.
No. We've got to move that over. Make this 1.04 times 10 to the... Are we going to add 1 or subtract 1?
No. Add 1.
Add 1. This number got smaller, the power gets bigger. Negative 9 plus 1, negative 8. So let's look at subtraction. So 5.8 times 10 to the 9th minus 2.7 times 10 to the 9th. Remember, subtraction follows the same rules as addition. We must have the same name. And then we're going to combine the counts. 5.8 minus 2.7 is 3.1 times 10 to the 9th. Good. Well, what if I have 6.38 times 10 to the 13th minus 5.94 times 10 to the 13th. So I have the same name. I can go ahead and subtract. What is 6.38 minus 5.94? It is 0.44. Good. Times 10 to the 13th. Now, of course, it's not going to stay like that. We've got to change this. We have no non-zero digits in front of the decimal point. So we're going to move that over to be 4.4. Now, this time the number got larger. It went from 0.4 up to 4. So the power has to get smaller. 13 minus 1 is 12. So 4.4 times 10 to the 12th. So what if we have 8.73 times 10 to the negative 11th minus 7.89 times 10 to the negative 11th. We have our same power of 10 here. So we'll go ahead and subtract. 8.73 minus 7.89.
0.84.
0.84 times 10 to the negative 11. What do we have to change?
Change it to 8.4.
8.4, good. Now this time the number got larger again. The power has to get smaller. Negative 11 minus 1?
Negative 12.
Negative 12, very good. What if we don't have the same name again? What if we have 7.43 times 10 to the 9th minus 3.8 times 10 to the 8th? Generally, we'll still go to the larger of the two powers. Which one's larger? 10 to the 9th. So that one doesn't change. 7.43 times 10 to the 9th. This one's going to be times 10 to the 9th. So what does this part become? 0.38. The power got larger, the number gets smaller by 1 decimal place. So 0.38. We subtract 7.43 minus 0.38 is 7.05 times 10 to the 9th. Not so bad. So let's take a peek at this one. Oops, that's not what I want. 1.27 times 10 to the 12th minus 9.4 times 10 to the 11th. What power of 10 am I going to change everything to? The 12th. So this one's going to stay the same. This becomes 10 to the 12th. What's this number become? 0.94. Good. This time we subtract 1.27 minus 0.94 is 0.33 times 10 to the 12th. Now this one obviously has to change. It's going to become what? 3.3 times 10 to the 11th. Good. This got bigger. This has to get smaller. So 12 minus 1 is 11. Okay, let's look at multiplication. When we multiply, 1, we don't need the same name. 2, we combine the counts. And here's where we also combine the names. So let's start out with 2.5 times 10 to the 7th times 1.2 times 10 to the 13th. I do not have the same power of 10, but it doesn't matter. When we multiply, we don't need the same name. We could multiply feet times pounds. When we had fractions, we didn't need common denominators to multiply. With our scientific notation, again, we do not have to have the same name or the same power of 10. We're just going to combine the counts. What is 2.5 times 1.2? 3 or 3.0. Now we're going to also combine the names. So remembering what we learned about powers, what's 10 to the 7th times 10 to the 13th? When we're multiplying, we do what with the powers? Add them. 7 plus 13 makes
20.
20. Very good. So 6.4 times 10 to the 11th times 3.8 times 10 to the 15th. So we have to multiply 6.4 times 3.8. 24.32, good. Times 10 to the 26. Good. 11 plus 15 is 26. Now, just like before, we've got to change this. This is going to become what? 2.432. Now, that number got smaller, so the power gets larger. So 10 to the 27th. So we may have 3.9 times 10 to the negative 9th times 4.1 times 10 to the 12th. We combine the counts. What's 3.9 times 4.1? 15.99. Good. Times 10 to the third. Perfect. Negative 9 plus 12 is 3. Positive 3. And of course, this changes to what? 1.599 times 10 to the 4. This number got smaller, so the power gets larger by 1. Perfect. Or if we have 7.2 times 10 to the negative 12th times 4.5 times 10 to the negative 5th. 7.2 times 4.5 is 32.4 times 10 to the perfect. Negative 7 and negative 5 make negative 17. And that's going to change to what? 3.24 times 10 to the negative 16. Good. This got smaller by 1 decimal place, so the power gets bigger by 1. We could divide. using the same rules as we did with multiplication. 1.728 times 10 to the 8th divided by 1.2 times 10 to the 5th. We divide the counts. 1.728 divided by 1.2 is 1.44. Then we divide the names. 10 to the 8th divided by 10 to the 5th. 10 to the 3rd. We subtract the powers. Good. We might have, let's see here. 1.024 times 10 to the negative 8th divided by 2.56 times 10 to the 5th. We divide the counts. 1.024 divided by 2.56 is 0.4 times 10 to the, it's negative 8 minus 5, which is negative 8 plus a negative 5, negative 13. Good. Now, of course, we're not done there. What do we have to do? So 4 times 10 to the negative 12. Good. This got large. Oops, sorry, it's not negative 12. What is it? Negative 14. Thank you. This got larger, so the power has to get smaller. Negative 13 minus 1 is negative 14. Let's see here. We have 2.4 times 10 to the 9th divided by 5.76 times 10 to the negative 6th. What is 2.4 divided by 5.76? We'll go to 3 decimal places if it's longer than that. What'd you get? 0.416 times 10 to the, what is 9 minus a negative 6? It's 9 to the 15th. Good. Subtracting a negative makes it plus a positive. Yep. So then this becomes 4.16 times 10 to the 14. Good. This number got larger, so this has to get smaller. 10 to the 14. Okay, before we do any more with this, I think it is time to stop and let you guys do your quiz. I'm going to give you some homework here out of the book. This is in the big book. It is page 205, exercise 6-12A, 1 through 15, the odd. Then also on page 205, exercise 6-12B. That's also 1 through 15, the odd. Now the quiz is mostly on the powers and roots from last class. There's a little bit converting scientific notation, but no operations with the scientific notation yet. We will go over that again on Wednesday a little bit, and then we'll talk about powers and roots with scientific notation. Then, of course, next week we don't have class on Friday, do we?
You know what, Mr. Al, we're not going to, I sent you an email, we won't have Wednesday either, because these guys have gone to trooping.
Oh, okay, so it'll be next week, we got the week off, so it'll be a week from next Wednesday. Perfect. Also, Mr. Berghammer, are you aware of our spring break coming up?
Yeah, I can't remember the dates exactly, but I do have them.
Okay, yeah, so March 20th through 24th, there won't be classes that week.
Okay.
Just wanted to make sure you were aware so you didn't expect to have me fill it in some time for you. Okay, so I'll give you the rest of the class to start on that homework and to work on the quiz. Again, do the quiz first. And we'll see you in a week and a half.
All right, thank you.
You bet.